Over this past year, I've been building a mechanical device to speed up the process of putting t-shirts on hangers in an industrial application. I'm addressing this issue because a large-scale automated process like Goodwill's clothing department benefits from saving seconds off of a highly repetitive task done thousands of times a day. What once was a school assignment has turned into a year-long passion project. The main idea behind the device is that hangers will be stored in a mannequin-like compartment until someone pulls them out from the top. Then some mechanical energy will be used to push the next hanger into position.
The main problem with the device is that it has to be mechanically powered. This
has been hard to fix and has caused the project to result in a multitude of failed prototypes and setbacks.
The model's gone through many design iterations, but for the sake of this video, I'm going to stick with the current medium.
Originally, the mechanisms were prototyped in Lego and then the model was made in wood. These models weren't precise enough, so I switched to 3D printing. For the mechanisms, the plan was to make an input that would turn in both directions but have a mechanical pawl pressed on the gear to guide the direction of rotation. This is fed into a mainspring which releases after a certain amount of rotation. Then the power would be transferred into a two-way one-way rotation differential so I could get double the rotation in a given direction. Lastly, power from the rotator goes to the axle with which the belt sits upon. However, the input differential failed by not releasing the power from the mainspring and forced me to reconsider the purpose of the input mechanism.
I decided I needed a model that would wind up in the clockwise direction
and then rotate freely when turning counterclockwise. This is when I discovered the YouTube channel Winter Gaton, who is building a marble machine with the exact mechanism I needed, a torque limiting flywheel. I manipulated this mechanism to satisfy the criteria for my input. Now it's a gear with marble latches to press against the plate until the maximum force is reached and causes it to rotate in the opposite direction. This design led me to the first milestone of the project. The machine could run through the mechanical motion that it was required to do. However, it was an ideal situation where the belt doesn't even exist. Once the belt was applied, it quickly became apparent that the model wasn't going to work as the gears stopped rotating. The problem with the belt was that it was too heavy. However, I know that there's a torque-gear ratio relationship where T in over T out equals the gear teeth in over the gear teeth out, which equals revolutions in over revolutions out. These equations were derived from the torque equals R cross F, distance cross force relationship in the gears, which means that I can adjust the gear ratio to increase the amount of torque being applied to an axle. After some calculations, I discovered that a 4-to-1 revolution reduction would make it so there's enough torque for the belt. To compensate for moving the hanger upward and increasing the rotation, I discovered I needed to make the input gear ratio 6.67 to 1. I ended up meshing a 24 to 8 tooth and a 20 to 9 tooth gear to get the rotation I desired. However, I did not recognize that this meant that there would be a torque reduction of 6.67 to 1 on the gearbox, which is problematic since that meant there wasn't enough torque to turn the gearbox, and I had to start again. In the next iteration, I had to redesign some of the initial goals of the device. Instead of moving the hangers up the track, I realized I could just drop the hanger into a designated spot and pull them out against a release mechanism. Since I am building new mechanisms on top of old models, the complexity of my mechanisms increased. I was challenged with finding a precise way to drop the hangers in even intervals, moving the energy from the input to the output, and releasing energy stored in the mainspring. I have since addressed these issues with a constant force reservoir, a gear train, and a self-starting Swiss lever escapement.
I hope to see this model be introduced into natural environments someday, but until then I will cherish the design process that comes with designing the parts.
Several problems that I will have to address in the future include correcting the hanger dropper so the hangers don't bunch up on each other. I need to find a new material for the mainspring as it breaks at the same spot because plastic is not an ideal material to apply stress over time. I will also need to create some sort of overcorrection mechanism because my mechanisms are not very efficient, so the efficiency will need to be compensated for.
One of the key takeaways to gather from this journey is that while there are an infinite number of problems associated with designing a mechanical device, there are just as many solutions if given enough time.
For example, the input mechanism from the wooden model is an efficient design. It just wasn't feasible in a large wood prototype. Watches use them to govern where to store energy based on turning it in the clockwise or counterclockwise direction.
Most importantly is to have fun with the whole process, for without it, I would have given up a year ago.